Thank you for the introduction. So I want to start off by mentioning that this is joint work together with Fabian Stemmler, who was a master's student in our lab, and also with Julian, Erhard, Tilscher, and Helmut Seidl. And let's start off very easy. Most of you will be familiar with this. So when we do static analysis, we have to do the option to do something that we call a flow-sensitive analysis. And in such an analysis, we would compute basically one piece of information, say from some abstract domain D#, for each of the program points that we have in our program. Sometimes we find this to be expensive, and then we can alternatively go for something that we call a flow-insensitive analysis, and then you would just compute one global piece of information that needs to hold throughout the entire program. However, this is not the only thing. There's also some middle ground between those two things, namely something that we have dubbed mixed flow sensitivity. And the idea is that you are flow sensitive for some information and flow insensitive for another class of information. And then one could say that for the flow sensitive information is associated with something that one calls the locals, and the flow insensitive information is associated with some set of things that one calls the globals. Now there's many instances of this. One of the instances that people might be familiar with is, for example, when you do global store widening, but you don't do it to all variables, but just some of them. Another instance that people might know is that something like this can be helpful when you're doing an efficient yet precise pointer analysis. It also arises when you're sort of analyzing unusual control flow. And it also arises when you want to have a way of expressing different types of having context in your analysis, and you want to have a very flexible framework for it, then it can also be helpful. And perhaps the most common instance of this mixed flow sensitivity is when you do a thread modular analysis of the values of multi-threaded programs. And this is also where we'll be drawing the example from here. So when you do this, then typically you would say that your flow sensitive information is per program point. So your set L would be the program points, and your flow insensitive information you would organize by program global variable, and so your set G would be the global variables of the program. And then one simple idea is that we would flow insensitively accumulate all of the possible values that these global variables can have. Now, if you have powerful abstract domains that have infinite ascending chains, then you have a problem here, because you cannot just accumulate all of the possible values that you might see or their abstractions, because it might not terminate. So you might need to use something that is called a widening to ensure that this entire thing terminates. So let's take a look at an example. So here we have a relatively simple multi-threaded program. It has two threads. One of them is always increasing I if it's less than 10, and the other one always decreases I if it's greater than minus 10. A variable A is the one that's being modified. So here we would expect that at the end, an invariant for this A could be that it's between minus 10 and 10. So let's take a look at what an analysis might find. You would start analyzing somewhere locally, and then you would find the first contribution or first possible value of A. And if you're doing an interval abstraction, then you would abstract this value 0 here with this interval from 0 to 0. So you would record this contribution, and then you would continue your analysis, and then you read this value of A into your local I. You check the guard holds, and then here you cause another contribution to this global variable I. In this case, this would be the interval 1, 1 that you contribute. And now we said to ensure termination, we are always applying widening here. So we immediately get an interval that goes from 0 to infinity. Now, of course, this value of A has changed, so we need to evaluate this loop one more time. But here, nothing more happens. The value is already subsumed. So at some point, we move on to the other thread. In the other thread, we also read this value of A. We check the guard, so there are values that pass this guard, and then we subtract 1, and this is our new contribution to A. So we find that the contribution to A is in the interval from minus 1 to infinity. We combine this by widening again, and then we have the top interval, which we have arrived at. So it's nice, our analysis terminated, but also it is actually not what we hope to find out. So actually it turns out that widening at these globals can actually lead to a drastic precision loss at the globals. Now, of course, the problem with widening is not new, so people have proposed solutions. And actually, it was even Couzeau and Couzeau who proposed, okay, if you do widening, then you maybe also need to do narrowing to go back down with the values. So one naive idea might be to say, okay, I just apply narrowing, and I narrow the value of the global with whatever was the last contribution. However, it turns out that you cannot do this. So this is because this value will actually be too small. So what we need is, we need a better idea to apply widening and narrowing for these globals. And the idea later will be to do this per origin, where the contributions come from. Now, initially we said, okay, let's integrate it into our framework, but then we realized that there's a whole zoo of frameworks that somehow support this mixed flow sensitivity. So you can either formulate it as some sort of nested fixed point algorithm. Some people have proposed something that's called a blackboard architecture. Our group has at some point proposed these side effect and constraint systems. So we thought it might be nice to actually be able to have a solution that works for all of them. And to do this, we would like to decouple handling the updates of these globals from the rest of the solving mechanism. And we do this by what we call update rules. Now we need to make some mild assumptions about what the solver does. And our assumption here is that the solver internally has some map row that maps the globals to the abstract values that you have for them. And the crucial thing is, we say that the solver itself, it can read this map, but it cannot modify it. The modification of this map, it delegates to something which is this update rule. And this is the signature of such an update rule. And the idea is, whenever the solver has computed a new local value, it will call this update rule, providing for which local the value was computed, so the origin, then it would provide a set of new contributions and the current map row. And then this update rule would give you back a set of updates that then need to be applied to the solver, to the row. So if we recall our update rule from earlier, where we just always proposed widening, it might look somewhat like this. So we go through all of the contributions, we see if the contribution is subsumed. If it is, we don't need to do anything. And if it's not subsumed, we perform a widening between the new contribution and the old value that we had in row, and then return an update for it. Now we also want our analysis to be sound in the end, so we need to think about how this solver and the update rule actually interact with each other. And here we have this theorem from the paper that a hosting solver with a sound update rule returns a sound result whenever it terminates. Now there's two terms here that we should probably talk about. The first one is hosting solver. What do we mean by this? Well, the first property is this thing that I mentioned. It's not supposed to modify this row itself, but always rely on the update rule for the updates. And the second thing is we need it to be robust in some sense with respect to the values of the row. So if the row always subsumes all latest contributions to the globals, then the solver needs to compute a sound result. This is the requirement that we have for a hosting solver. And then the counterpart is what do we require of the update rules. And there we say a sound update rule is one that if you have a sequence of calls to update globals, the returned updates, if you have any, will always subsume the latest per origin contributions. And whenever you have a contribution that's not already subsumed by row, you will produce an update. And then when you put these together, you get our final theorem. Now recall that our idea at some point was to apply widening and narrowing per origin. So let's see how this could be written as an update rule. And here we have this map, C map, where we borrow the static semantics from C. And the idea is that this is some internal state of the update rule, but it persists through the calls of the update rule. And in this C map, we record the last contribution that we have seen, and then whenever per origin, and then whenever we have a new contribution from some origin, we compare whether it is subsumed by the old one, in which case we perform narrowing, or if it is not, then we do widening. And then the new value of the row, or the update to the global, we obtain simply as the join of all of the entries. This looks a bit complicated, so let's do an example. So this is our example from earlier. We have, on the right, we have row, and on the left, we have the internal state of this update rule. So recall, we start the analysis somewhere here, and then our solver will call this update global with the origin U1 and this contribution of the interval 0, 0 to A. So we record this in our map, as we have not seen this contribution yet. And then to get the new value for A, we join together all of the things that we have in this map. So we produce an update with the value of 0, 0, and this then becomes the new value of row. Now at some point, the analysis continues inside of this loop. It will then read the value for this A, which is 0, 0. It will go through the branch, and it will produce a contribution from this origin U6 with this interval 1, 1. So we record this again in our map. Nothing too interesting. We join these things again together. We get the new value of the new interval of 0, 1. And then, of course, this A has changed. So later we will evaluate this loop again. and we will once again go in this guard. We will then find that now the contribution to A from this U6 is this interval from 1 to 2. So we take those two, as it's not subsumed, we apply a widening here. So we get an interval from 1 to infinity. When we join those two things together, we get the new interval for A that's from 0 to infinity. And then we do one more iteration. In this iteration, we will now take a look. We read the A, we apply the guard, and then we increase it by 1. So we will find that here the contribution from this local U6 is this interval from 1 to 10. And then now as this interval is subsumed, we will apply narrowing here, which gives us this interval from 1 to 10. If we combine them together, we end up with the interval from 0 to 10. And this is also the update that we produce. So we iterate the loop one last time, but we find that here we have reached a fixed point. So at some point, we then move on to the second thread. We read the value for A again. We check the guard. We find that here the contribution from this origin U13 to A is between -1 and 9. Now this is an entry that we don't have in our map yet, so we add it. We compute the new value as the join of all of the things. We have an update to this global A, and A has changed, so we reevaluate the loop once more. We go in here, we find that now the contribution is from -2 to 9, so it's not subsumed, so we need to apply widening once more. We end up with this value of -infinity to 9 in here, which gives us an update of -infinity to 10. There's also no new value of our A, and then we iterate one more time. Here we now find that actually this A is bounded, or the update to A from line 13 is bounded from below by -10. And now this value is subsumed, so we can apply narrowing again, which gives us this interval here. And if we join all of them together, we find out that the interval is actually the interval from -10 to 10. And then we would, of course, need to iterate everything one more time, but this is actually the fixed point that we wanted to reach. So what we have seen is we are able to do narrowing when the contributions from some origin shrink, which is nice. However, there's another problem that we encounter, and this is what we dub the problem of toxic trash. So consider this example program here. You have once again one global, and you have a sort of complicated loop in one thread, and the other thread you just check basically that the global has not been written. And here the problem is that while we are locally iterating and trying to find a solution, we do widening of this loop. So at some point we will consider this contribution of 42 to this global A. However, later on we will find that this is actually not reachable, this line 6. So the contribution that we have recorded for A is trash because we would not need it. And it's not just trash, but it's also toxic trash because it causes an assertion that we were interested in this thread 2 to now fail. Now, how can one get rid of this toxic trash? And the idea actually here is surprisingly simple. It suffices to make contributions that are no longer happening explicit. So we basically wrap our update rule in another update rule that records for the last time when I evaluated this, which unknowns received contributions. And if now something doesn't receive a contribution anymore, I explicitly record a bottom contribution, which will then cause a narrowing and which will cause this toxic trash to disappear. So inside of the paper, we have several things. So what we've seen here is update rules that allow the values of globals to shrink. We have seen a form of abstract garbage collection to take out the toxic trash. In the paper, we also compare with an existing approach by Apines and colleagues, which was deeply intertwined with one solver that we casted as an update rule. We also give a detailed soundness theorem for the update rules. And we also consider the notion of properties that the update rules need to have to ensure termination of the analysis. And it turns out that there one needs an interesting property that is somewhat stronger than what you would usually have for a widening. The other thing we have in the paper is an experimental evaluation. So we do have a little bit of time to quickly touch on that. For our experimental evaluation, we implemented the update rules within the static analyzer Goblin, which is a static analyzer that targets real-world multi-threaded C programs, and it's based on abstract interpretation and side-effecting constraint systems. We did several evaluations. One of them was on context-insensitive analysis for this software verification competition reach safety benchmark set. And there we compared with a built-in strategy of the Goblin system, which is a little smarter than the strategy we've seen where we always widen, but not by that much. And we evaluated along two axes. One of them was the precision, and what we considered as a precision measurement here was something that we call the net impact. So we looked at the analysis results with the update rule and without the update rule, and compared the abstract values of globals and locals. And we basically counted how many globals were improved, subtracted those where the result got worse, and then divided this by the total number of locals and globals that you have in the system. And we were quite happy to find that actually there is a net precision gain for 52% of the tasks. And for 20% of the tasks, it's also somewhat substantial. So it's more than 5% of unknowns that are actually improved. However, there's a downside. We also had a net loss for about 2% of the tasks. So in some cases, our smart update rule actually makes things worse. The other interesting metric is always how is the runtime. And here we found that the overhead was not too terrible. So we had a 3% average overhead over the baseline, which is a price you might be willing to pay to get more precise values for the globals. So to sum things up, we have seen that mixed flow sensitivity is a nice middle ground between flow sensitivity and flow insensitivity. We have seen that one can use update rules to decouple the handling of globals from the rest of the solver infrastructure. We have seen update rules that can recover precision. And we have also seen a technique for abstract garbage collection that takes out the toxic trash. And finally, we have taken a look at the experimental evaluation on SVComp. And in the paper, we also consider a large set of real-world programs. So with that, I'd like to thank you for your attention, and I look forward to any questions.
Questions? Okay, thank you. So in your initial example, one other technique that could help improving precision would be to use some kind of, well, better widening, like for instance with thresholds or to find a way to widen a little bit more slowly.
Absolutely,
Did you
yes.
compare with such techniques and see where you do improve better or less, or when you can combine your technique with that?
So with widening thresholds specifically, we did not compare. The framework in principle supports them. However, here we were shooting for a general solution. And with this widening thresholds, it's somewhat hard sometimes to determine what the threshold should be. So here they were constants, but quite often they might not be constants. What we did compare with is a widening delay. So I think a widening delay of 3 or something, it also improved things, but then there was an additional improvement when we considered our update rules here.
Sure, thank you. Another question?
I don't have a deep understanding of this analysis, but I have a naive question. So based on the experimental results, you have some improvement over the standard analysis implemented in the Goblin and some loss of precision.
Yeah.
If there is a way to combine these two techniques and to get best of both worlds.
There might be a way to combine these two techniques, yes. So it actually turns out that this precision loss, the case where we lose precision mostly goes away if we combine it with a widening delay. So basically the effect where we see these precision losses is due to the update rule, the default update rule in Goblin being a little bit smarter than the one I've presented here.
Yeah, I thought that maybe some way of improving precision would be to do some kind of policy iteration where you could do the analysis on one thread, widen on one thread, and then narrow on this thread. And then when we reach a fixed point, you can switch to the other thread, do the same thing. Can we describe your technique as a way of doing that, but without committing to a single fixed point strategy?
Yes,
how would it relate to that?
Yeah, I would think that the strategy you've described is an alternative strategy and it would work, but as you've said, it's somehow fixed to this fixed point strategy where you sort of locally iterate the thread to a fixed point.